Bismillahirrahmanirrahim. In today's video, we will be going over what structures are there when two atoms bond together. We already know the structure of an atom from the previous class, and now we will be discussing about the structures themselves of the bonding, atomic bonding structures. Now, first of all, we need to understand why exactly do they bond. Well, they bond because they do not have a complete shell. Their incomplete shell is the reason why they bond in the first place. And when they do that, what happens is that this allows them to complete their shell. So group 1 have 1 electron in the final shell, group 3 have 3 electron in the final shell, and group 7 have 7 electron in the final shell. So their group number tells us how many electrons they have in the final shell, and none of them have a complete shell except for the group 8. Group 8 have complete shell electrons. In order to complete this valence shell, they bond with other atoms. Now, this is divided into three portions: covalent bonds, ionic bonds, and giant metallic bonds. Ionic bonds are bonds that form between metals and non-metals. We've already gone through the separation of metals and non-metals, and we can get that information from the periodic table. So here we have the periodic table. Mind all of the extra information there, but the blue sections represents metals and the red sections represents non-metals. There is a specific line for metalloids also there, but for now all you need to know is that the left hand side or the blue section is for metals and the right hand side is for non-metals. If these two bond together, they form an ionic bond, and this bond is formed when an electron is given or taken away from an atom. So the metals form positive ions because they have less than 4 electrons, so it is easier for them to lose 1 electron and form the complete shell. That's why if we were to discuss cations, they are positive ions. All cations are known as positive ions, and those would be in NaCl, for example. Those would be Na is the positive or the cation, and Cl is the negative or the anion. Anions are negatively charged ions, and cations are positively charged ions. Positive charge on an atom represents lack of electron. So sodium, as it is of group 1, has given 1 electron to the chlorine, and this has given sodium the complete shell and also given chlorine the complete shell as well. Because chlorine has 7 electrons, it got 1 electron, so that means 8 electrons. It has fulfilled its shell as well. The ionic bonding is in a giant lattice structure. A giant lattice structure is a regular arrangement of positive and negative ions. This basically, the word lattice means regular arrangement, a patternized arrangement, a pattern of atoms. So here it is a pattern. We can observe a pattern, and that pattern is repeated, and that's why it has a giant lattice structure. And this giant lattice structure is made from positive and negative ions, and that's the reason why. The force of bond is electrostatic force between the ions, and this is a very incredibly strong force because they have a complete charge on them, and that complete charge is very strong, and that attracts them incredibly close to each other. So here we can observe that we have these particles that are incredibly close to each other. These bonds are incredibly close to each other. Keep in mind that Na is bonded to Cl, and that is a fact. And while that is a fact, in a giant structure, this Na or the positive ion is capable of attracting the other negative chlorines as well, and this strong attraction is the reason why they have a strong and high melting point. They are strong substances, they are brittle, and they also have high melting points and boiling points. Sorry. Now the syllabus asks us for us to realize how to create dot and cross diagrams. Dot and cross diagrams basically tell us the amount of electrons in their final shell. right? And here I have given you an example. Sodium does not have any electrons in its final shell, so I have not drawn any electrons in its final shell either. It has a positive charge, so I just got a bracket surrounding the sodium and placed a positive charge on top of it. Besides it is chlorine with all of its electrons labeled in dots and in the color red, and it has a negative charge, as you can see from right there. And this attraction between them is quite incredibly strong. Now let's try to make this dot and cross diagram for other atoms. How can we do that easily? Is by realizing an easy step to do that. Right? So there are two methods for us to evaluate that. Let's first of all do an easy one. So for example, here we have this third question. This is an easy question, and lithium is of group 1. All right, it is of group 1, and bromine is of group 7. So as lithium is a metal, right, it is a metal, it will form a cation. It will lose electron. How many electrons does it need to lose? It needs to lose 1 electron. If it loses 1 electron, then it must also be capable of satisfying bromine. If it is capable of satisfying bromine, then it has made its complete structure, and that's why its molecular structure is like that. So it would form lithium bracket positive and bromine with all of its electrons shown in dots. It is not necessary that you pick dots. You can pick either dots or cross, but they need to be separate. So the electron for lithium must be represented as the opposite sign as it was labeled for the bromine. So this would be, for lithium, would be a cross. This would be negatively charged, and this is the dot and cross diagram for lithium bromide. Let's continue and look at calcium iodide. If we have calcium iodide, then we know that calcium is of group 2 and iodine is of group 7, right? That means that calcium has 2 electrons and iodine has 7 electrons. So we can understand that calcium will have no electrons in its final shell, and it will have a 2 plus charge. Because it has lost 2 electrons, it will have a 2 plus charge. It has lost 2 electrons, and that's why it has a lack of electrons in its atomic structure, and that's why it has a 2 plus charge. And if we were to make diagram for the iodine, it would look something like this. But this has only filled 1 electron. Basically, calcium has provided 1 electron to this. So where is the other electron going? Well, the other electron is going to another iodine, and we can copy paste that like so. Right? So this is the structure for calcium iodide. Let me just expand this so that it is much more easily represented. Okay. Similarly, the situation here is the same. So I'm just going to copy this, except I will only be taking the small changes, like taking this out. So basically what I want to do is, let's take this calcium and place it up there. Let's take this iodine and place it up there. Now why I did that? I did that because they are in the same group. Magnesium is of group 2, so I can just replace that with magnesium, and chlorine is of group 7, so I can replace this with chlorine as well, and this as well with chlorine, and this will be the complete structure. Now let's get on to Al2O3. Now this is a interesting question. How would we evaluate that? Well, we can imagine it in terms of this. So first of all, we must be capable of realizing how much charge of an ion will be there. Aluminum is of group 3 and oxygen is of group 6. So aluminum must lose 3 electrons and oxygen must get 2 electrons. Because of its lack of electrons, it must get 2 electrons. Now it will have a complete shell. And that means that if we were to draw the structure, it will be a little bit large. So I'm just getting space. Aluminum, there will be 2 aluminum. And each of them will have a 3 plus charge. No need to show the electrons, they are already gone to the oxygens. Let me erase this. And now we can have our oxygens like so. With their final shells. Now, oxygens originally have 6 electrons, so 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And similarly here as well. And the other electrons must have been received by the aluminum. So we can just cross those out. This is the electrons from the aluminum. Now, a lot of the times we are actually not told the molecular structure. We know this information right here. We know this information and we know this information, and we are supposed to get this molecular structure from that. So let's try to understand how we can do that. So the easiest way to get that answer is to have written down your charges and your symbols, right? The next thing that you will do is take this charge, right, this charge right here, and you will take this charge and exchange it to this position, and you will take this charge and you will change it to this position right here. Make sure to remove the signs. Remove the signs. So the positive and the negative signs must go. We will again get Al2O3. Let's do another example. Form an equation, form a molecular structure of magnesium with oxygen. What would it be? Well, I know that magnesium has a 2 plus charge because it is of group 2, and oxygen has a 2 negative charge because it is of group 6. So it will need 2 electrons to fulfill its shell. This will go right there. Let's make a better arrow. This will go right there, and this will go right there. We will get Mg2O2. But we can furthermore simplify it, and we will get MgO, and this is the structure of magnesium oxide. So you can do it both ways. You can have a molecular structure and form this dot and cross diagram, or you can have these charges and form the molecular structure as well. So let me just arrange these in a better way so that they are looking much better at the document. All right. So let's continue onwards and see what is in store next. So this was the understanding of ionic bonds. Now let's understand what the physical properties of these are. They have a high melting point and a high boiling point because they have a high force of attraction due to that electrostatic attraction between the oppositely charged ions. So these charged ions are highly attracted to each other, and that's the reason why they have a high melting point or boiling point. Compounds are brittle. The reason why they're brittle is because of the fact that they have a high and very strong force of attraction between each other. They cannot slide over each other. And I'll rephrase when I get on to substances that can be bent and that can be used as lubricants as well. You will have a much better understanding in those scenarios. So let's keep that brittle point in mind and we will understand it furthermore later on. Ionic bonded substances can conduct electricity in liquid or aqueous form. That is a very important um, point, because this can identify an ionic bond, because this is exclusive. This is a very um, special characteristic for ionic bonds. These are the only type of bonds that are capable of conducting electricity while they are in liquid or aqueous form, especially in aqueous form. While metals are capable of conducting electricity in liquid as well as solid forms, the ionic bonds or ionic bonded structures are very exclusive to this property, and they are very poor conductors of electricity in solids, while otherwise metals are good conductor of electricity in general, whether they are in solid, liquid, or in aqueous forms. So that is a fact, and that is a very unique thing, right? So this point of liquid or aqueous is very important. They are very poor conductor of electricity in solid form. Keep that in mind. Covalent bonding. So covalent bonding is the bonding due to non-metals bonding together. In this type of bonding, they share pair of electrons between them, leading to a noble gas structure. Again, the structure that has a complete shell. Electrostatic force due to the electron shell. Now let's make a couple of structures and let's understand these couple of structures forming about, right? So let's make the structure for hydrogen, right? Let's make the structure for hydrogen. So how would we evaluate how many bonds there will be, and how, first of all, how would we represent a covalent bond? Well, a covalent bond is represented by a simple dash. So this dash represents a covalent bond. And furthermore, this bond can be shown in terms of the dot and cross diagram, and that would be looking like so. So how did I even conclude that hydrogen would have a single bond? Well, I would look at its structure. Hydrogen is of group 1 and it is of period 1 as well. It is a gas, it acts like a non-metal. So it needs one electron. Hydrogen has a requirement for one electron needed. So the amount of electrons that they need is the amount of bonds that they will make. This is a fact. So that is equal to one bond made. Also note that this is separate electrons that are being shared. So one is being shared by the other hydrogen and one is being shared by the other hydrogen. So this is how you would represent the bonds for hydrogen. Let's do some other substances. I will do structures for, let's do structures for this, and you guys can do it for the rest. All right. So in order for us to create carbon and oxygen bonds, we already know that it has one carbon and two oxygens right there. Now, how do we know how much bonds it will make? We will look at its group. Carbon is of group 1, sorry, it is of group 4 and this is a for group 6. If it has 4 electrons as it is in group 4, it needs 4 electrons more to complete its shell. So carbon will be making 4 bonds. It needs 4 electrons, it will make 4 bonds. Oxygen is of group 6, it needs 2 electrons, so it will make 2 bonds. All right. So by that logic, you can evaluate that 1 and 1. This is a structure of carbon dioxide. As you can see, carbon has fulfilled its demand of 4 bonds and oxygen has fulfilled its demand of 2 electrons for both of them. If we were to transform this into the dot and cross diagram, it would look something like this. So XOXO. This represents two bonds. This is a single bond, this is another single bond, and this represents in total two bonds. We can have that for oxygen, and then we will write the amount of electrons for oxygen. So oxygen has shared those electrons as well. So that means that if we were to say that X represents the electrons for oxygen, then it will have 1, 2, 3, and 4 electrons remaining. So if we were to count the crosses 1, 2, 3, 4, 5, 6, that means that yes, indeed, oxygen individually had 6 electrons in its shell, but it has shared 2 of its electrons, and so has carbon. So overall, oxygen has fulfilled its demand. Similarly, we can do the same thing here, and we will have a similar structure right there as well. Let's do the structure for ammonia or NH3. Nitrogen is of group 3. It needs, oh sorry, it is not of group 3, it is of group 5. My bad. It is of group 5 and hydrogen is of group 1. Nitrogen needs in total 3 bonds, and hydrogen is, as it is of period 1 as well, it has one shell, it needs one bond or one electron. So the structure that it will form is N bond N and N bond N. You can substitute these bonds with the pairs. So this would be X dot X dot and X dot. And for preferences, I'm going to say that the dot represents the electron for nitrogen. So the remaining electrons that nitrogen has is 1, 2, 3, 4, and 5. So this is the structure for that. We can do a similar thing for oxygen. This would make a bond of like so. As you can see, oxygen has fulfilled its 2 bond demand, and so has hydrogen. So this would be a little bit like this, and let's say dot represents the electron for oxygen. This will be the structure or the dot and cross diagram for H2. All right, now let's move on to its properties. Okay, so the properties are of these are low melting point and boiling point, poor conductor of electricity and heat because they have weak intermolecular forces. So this point must have been at the top because this represents melting and boiling point, my bad. But they are poor conductor of electricity and heat as well because they are in gaseous form, and gases are not that good conductors of heat, and furthermore they are bad conductors of electricity because of the fact that they do not have any electrons to pass through from one point to another. Now, a subset of covalent structures are giant covalent structures. These structures are very special due to the fact that they do not have intermolecular forces. Well, they do a little bit, and some of them, but they are a little bit different. So let's see, what do I mean. So if I were to make 2 molecules of nitrogen, just for preference, if I have 2 molecules of nitrogen like so, they will not form a atomic bond, they will not form a covalent bond. No, they will be attracted to each other by a thing called intermolecular force, and these dots represent, these dashes represents those. This is quite weak. This is weaker than covalent bonds as well as ionic bonds. So ionic bonds are the strongest, covalent bonds come next, and these dotted or the intermolecular forces come next. All right, so by that logic you can imagine that as giant covalent structures are many covalent bonds formed to create a giant structure, then you can imagine that they will have high melting point and boiling point. So we have 2 structures right here looking very well. So here we have on the left diamond, and diamond is a giant covalent structure of carbon. So many carbon atoms have bonded together to form this diamond. All right, and hence this is an element. Many elements are diamonds. So as long as there's one type of an atom present together, that is considered an element. So this is an element, and it is a single type of atom present, which is carbon. Properties of diamond is high melting point, as they have strong covalent bonds. All of them are strongly covalent structured, and furthermore, this structure is not complete. Keep that in mind. This structure can continue onwards and form even more bonds. So this can form even more bonds. So this is another carbon, right? So it can form three more bonds, this can form three more bonds, this can form three more bonds, and so on and so forth. And this pattern continues and continues and continues, and that's the reason why this is a giant covalent structure. So the properties explain that hard and strong bonds don't break or slide easily. Used in cutting tools. Again, the sliding part is discussed later on when we discuss things that can slide over each other. Silicon oxide have similar properties, high melting point and boiling point, as all atoms have strong covalent bonds. And the similarities that they have is that they have a similar pattern, and they have a similar pattern that is represented by a tetrahedral. Tetrahedral is a type of shape, and that shape is common between both of them. As you can see that this pattern is quite common in both. And this pattern and type of shape, this type of shape, as you can see, this is like a pyramid. This looks like a pyramid, but it isn't. It is known as a tetrahedral shape, right? So furthermore, they have a similar bonding. Silicon has 4 bonds that must be made, oxygen has 2 bonds that must be made, and in carbon, carbon must have 4 bonds that must be completed all around. Hence they have strong, and they are very strong, they are very hard, high melting point and boiling point, inert and non-reactive as well, because they do not have any demand or any requirement to fulfill their valency. They are already fulfilled, and they do not have any requirements in that department. Let's continue onwards into the final giant covalent structure that is in your syllabus, and that is known as graphite. If my software can properly load, I will show you graphite. Now, graphite is a very special type of giant covalent structure. This is the pattern, and as you can see, it has quite a unique structure as well. Let me just lock this down so that it does not get deleted. Now, the thing is that it is in layers. This is number 1, this is layer number 1. Let me just take a different color. This is layer number 1, this is layer number 2, and this is layer number 3. So this is in a layer, right? And this layer is basically having those intermolecular forces. Recall those intermolecular forces between the molecules. This is what this molecule has as well. And this sliding pattern allows it to be used as a lubricant. Okay, so it is used as a lubrication. Layers can slip over each other. They have very weak bonds of attraction between the layers. All right, keep that in mind. Between the layers, not between the carbons themselves. And furthermore, it has a very unique property that it is capable of conducting electricity. And now, why is that? The reason why is because if you look closely, and if you pick a carbon that has all of its valencies shown, obviously, then that can be observed from this. So this and this and this and this carbon as well, this carbon as well, all of these carbons are showing all of the bonds that are possible, the maximum amount of bonds that are possible. So as I said, these covalent structures, or these giant covalent structures, don't show all of the bonds that are present. So this carbon will have made another bond, this carbon would have made another bond, and oh sorry, this would have made 2 more bonds, and this would have made 2 more bonds as well. Also, 1 bond, yeah, 1 bond, 1 bond, 1 bond, 1 bond, and so on and so forth. And this continues onwards and onwards. So we must pick a structure or a bond or an atom that is at the center, that shows all of its bonds being formed. So I picked this one, and this one, as you can see, has 1 bond, 2 bond, and 3 bonds. And this is weird because this is also carbon, and carbon usually forms 4 bonds. Where is this 1 bond going? So what happens is that this carbon is capable of letting its electron go and delocalizing it, and this allows the conduction of electricity. So it is capable of conducting electricity due to the delocalized electron, and this specific wording is demanded to you to get the mark. So if you don't use delocalized electrons, you will not get the mark for why graphite is capable of conducting electricity. Furthermore, it is capable of sliding over each other because it has weak intermolecular force. They are not very strong, so it is capable of being used as a lubricant. All right, let's check out the final structure. Oh, also this has a high melting point and boiling point as well, because it has strong covalent bonds between the carbons as well, so you must keep that in mind. Lastly, we have metallic structures. Metallic structures are very simple. They are structures that only form in metals. So metal and metals themselves have a metallic structure. All right, and this structure can be observed like so. So this is a structure for zinc and sodium, and this structure is basically capable of showing us what is happening. So as you can see, there is these positive ions, right? These positive ions, and these are represented by negative. So this is this little dot, this yellow dot is represented by negative electrons. So what you can say a metallic structure is, it is the structure in which positive ions are surrounded and electrostatically attracted to negatively delocalized electrons, right? So this is the structure of metallic. And now furthermore, in order to explain its properties, we must also evaluate all of the things. So first of all, these electrons are free to move. This is a sea of electrons, and as you already know, seas can of course flow from back and forth, and this electron is capable of going there, or this electron is capable of going there, and this allows them to conduct electricity. This is the reason why they have a delocalized electron, again similar to graphite, but this has a lot of electrons, a lot of delocalized electrons, so it is capable of being a very good conductor of electricity. Furthermore, metals are usually able to bend over each other. And now why is that? The reason why they are able to bend is due to the fact that if you put enough force, what happens is that these cations are capable of sliding, and they are able to go past or slide past each other. They are not basically bonded to each other, they're bonded or attracted to the electrons. So as the electrons are free to move, these large cations are also capable of moving if you provide enough force, and that force can be obvious and observed if you bend a metal. For example, if you bend an iron, it will bend instead of breaking apart, right? And this is why the properties are like so. And now let's just discuss it in terms of facts. So metallic bonding, the electrostatic attraction between positive ions in giant metallic lattice and a sea of delocalized electrons. They have strong electrostatics force, high melting point. That is the reason why high melting point and boiling point, hence they are also strong, but they can slide over each other. That's the reason why they have malleability and ductility. Malleability is the ability to bend, and the ductility is the ability to form wires. So lastly, we have delocalized electrons. They have delocalized electrons, they have a sea of delocalized electrons, they can freely flow from one point to another, and that's the reason why they are good conductors of electricity. So this is the final understanding that you are required to get from atomic structure. I hope this lecture was helpful and informative to you, and if it was, then perhaps it would be for others as well. So I hope that you would share it and like and subscribe to this channel. Inshallah, I will be uploading much more relevant and healthy content for you guys. So मेरी तरफ से अल्लाह हाफिज.